Eminent professors and learned participants, a very good morning to you. I extend a delightful welcome to the third day of one-week online faculty development program on emerging trends in pharmaceutical sciences, challenges from academic research to commercialization to empower us, the pharma fraternity, with the knowledge. Let us proceed with the session 4 of faculty development program. I humbly welcome the esteemed, meticulous, prominent, and august speaker of today's session and my guru, Dr. K. Kannan sir, Emeritus Professor, St. James College of Pharmaceutical Sciences, Chalappudi, Kerala, India, to deliver a scientific talk on the topic entitled Design of Experiments, a Powerful Tool for Pharmaceutical Research. Let us listen to the brief profile of Dr. K. Kannan sir. Now, I request the venerable, highly knowledgeable, admirable, to whom we always look up, Dr. K. Naveen sir, Professor, Department of Pharmaceutics and Biotechnology, to present the brief profile of Dr. K. Kannan sir. Over to Dr. K. Naveen Babu sir.
Thank you very much, madam. Good morning to all. It's my immense pleasure to introduce Professor Kannan sir, worked as head at Department of Pharmacy, Annamalai University. Currently, sir is an emeritus professor at St. James College of Pharmaceutical Sciences and SRM Institute of Science and Technology. Sir is having about 40 years of experience as an academician. Dr. Kannan sir has completed Bachelor of Pharmacy from Madurai University, Master of Pharmacy in Pharmaceutical Chemistry from Nagpur University, and Doctor of Philosophy from Annamalai University. Being as an academician, he always keeps on uplifting his knowledge by attending seminars and workshops, programs throughout his life. Dr. Kannan sir occupied several positions at Annamalai University as a chairman, Board of Studies in Pharmacy, chairman, Board of Examiners for Annamalai University, member of Academic Council, Annamalai University, member of Faculty of Engineering and Technology, member of Industry Institution Interaction Cell of Faculty of Engineering and Technology, coordinator of Entrepreneurship and Development Cell for Department of Pharmacy. He also served as an expert member in Union Public Service Commission, Government of India, New Delhi for recruitment of pharmacy related positions in Government of India. Served as an expert member to review research projects under Special Assistant Program of University Grants Commission. Served as Governing Council member for PSG College of Pharmacy, Coimbatore, serving as Governing Council of SBCP, Sivakasi. Sir has published around 85 papers, both nationally and internationally. He has guided 13 research scholars for PhD. For his meticulous work, he was awarded as a Pharmacist of the Year award from Indian Pharmacy Graduate Association for the year 2003. His area of interest is development and validation of analytical method for newer pharmaceuticals by HPLC, spectrophotometric methods, and also in making of pharmaceutical hard capsules,
Screenshots, please.
immunomodulatory agents, artificial intelligence in pharmaceutical research. Sir has received the grants from DST. He is the coordinator, DST FIST. He is the principal investigator for studies on complement system, alternate pathway, stimulant activity of selected herbal drugs funded by UGC. He is the chief coordinator for entrepreneurship, management and development cell, All India Council for Technical Education. He is the co-investigator of optimization of conditions for the economic production of pharmaceutical hard capsules from tamarind seed that is funded by University Grants Commission. He is the principal investigator of application of neural network concept to the analysis of multi-drug pharmaceutical formulations funded by AICT. He is the co-investigator of bioequivalence studies on chiral drugs employing from chiral HPLC analysis funded by AICT. Thank you very much, sir, for accepting our invitation. And today, sir is going to discuss on the topic design of experiments, a powerful tool for pharmaceutical research. Thank you very much for giving me this opportunity.
Thank you very much for your compliments. Shall we start?
Yes, sir.
Well, good morning to all. First of all, I thank the organizers for giving me this opportunity and keep me in the field even after my retirement. And in this session, I will try to explain some points about design of experiments. If you go by this design of experiment, I'll try to avoid all these the calculation part or your computational part or other things. We'll go basically the concept behind it and how to proceed with this. So now let us start with our basic, the current practice we do as a research in our institution or academic circle or in the industry. In this session, what we are going to see is what is design of experiment, where it can be used, why there is need for design of experiment, and what are the advantages of going for design of experiment, various types of design of experiment, optimization techniques, and with an example, I'll try to explain how to proceed with the design of experiment with a live example. Let us start. I want to develop a HPLC method. What we do in our college or even in industrial setup, we have to optimize the parameters. There are a number of parameters you have to consider. For example, qualitative parameters like columns. If you take column, we have again the size of the column, stationary phase used in the column, size of the packing material. So again, we have to decide which mobile phase, whether we want to go for single mobile phase or a multiple mobile phase, in which combination, and what is the type of buffer, whether you want to go for phosphate buffer or acetate buffer or formate buffer or whatever it may be, it depends upon the requirement. And is there any need for some other additives like peak modifier, ion pairing, inclusion complex forming agent? So these are some of the qualitative parameters we have to consider. Then on quantitative side, we have selected the mobile phase, but what is the flow rate? What is the percentage of solvent? We have selected the buffer, phosphate buffer, but what is the pH? What is the buffer concentration? Then after selecting the additive, we have to decide the concentration. Then we have to go for column temperature. So these are the various parameters we have to consider. Same thing for any type of research. If you go for developing a formulation, tablet formulation, you know very well. We have a lot of experience, so many choices we have to select from, and each selected excipient, what is the level of the proportion in the final formulation, what is the process condition, various process condition, those, like there's so many things we may have to fix or consider or we have to finalize. And after developing,
Sir, please
yes.
Enlarge the screen, sir. Full screen. Keep it full screen, sir, please.
It is full screen only. I think it is a full screen only. It's not full screen.
No, sir. It's small. Please proceed, sir. It's clear now, sir. No problem, sir. Please proceed, sir.
Okay.
Thank you, sir.
So next comes what we look for from this method. I want specific retention time. First peak I want after 1 minute at least, so that I can avoid disturbance from the solvent front. Last peak I want to make it as early as possible so that the runtime will be less. And resolution, the required resolution for baseline separation, peak symmetry, and theoretic break counter. Now, some of these parameters will have conflicting effect on the attributes. So many things we have to consider. But how we proceed normally, we do it by trial and error. By randomly, we decide the parameters and run the chromatogram. And if there is no satisfactory result, then we go for some minor changes here and there and try to bring the desired separation and carry on the result and go for validation. And we get the required procedure, required method, with which meets all the acceptance criteria, no doubt. But is it correct approach? It meets acceptance criteria, no doubt. And when you do this experiment like this, for example, I'm doing these 9 trial runs. First run, I take 40% acetonitrile at 0.4 ml per minute. Second at 50% and 0.4. Third at 50% 0.8. At 58% 1.8. Like that, I carry out various trial and tests. And I get a method. Among these 9, one is giving optimum result, and it meet out all the acceptance criteria as per the regulatory requirement. But it's not the best possible one. Now, the best possible one is somewhere here I have missed in the trial. Because I am choosing a random. So I will miss that optimal performance. This may be far better method than any other method I have tried. It may have a better resolution with shorter runtime, with lesser cost, and better weak shape. Though both the cases I'm getting acceptable result, but it is far better than the one I have optimized. And sometimes I may get the best possible one. But sometimes I will include some of the experiment here, and I may get the correct, the required one also. But it's not the complete of the work. Though it meets the acceptance criteria, though it is the best, and I need some more information about this process. If I do that randomly, I don't know what is the effect of each parameter on response. What is the effect of flow rate? How it influences the, say, retention time, say, resolution. How the pH changes the retention time or resolution. And again, I don't know about the critical parameter. Say some parameter may be very, very critical. For example, pH. Suppose if the pH I am selecting is somewhere near the pK value, a small change will have greater influence on the retention time and resolution. Same thing for any type of optimization, for even for tablet. There may be some factors which is more critical. A small change will greatly affect the performance or the quality of the product or process. So if I know that critical parameters, then while doing that experiment in future, or while manufacturing the product in future, I'll be careful, or I'll include as a part of SOP. Okay, these are the parameters critical. Be careful with that, or control these parameters meticulously, so that there will not be any failure. So this is important if anything goes wrong in future. In future, if anything is going wrong, if you have all the information at the development stage, you can easily rectify the problem and avoid the failure further. So next one is slightly improved method is change one factor at a time. This also some of us are doing. Keep all the factors constant and change any one at a time. And find out which is the best one. So that fix the constant. Then go for next factor. So like that, we go one by one changing it. still you get a satisfactory result. You say it is far better than random, but still it is not a perfect design. Here also, the problem is you may have to go for large number of trials, which may not be feasible. If they're having 9 or 10 factors, you cannot do it change one at a time for 9 factors. It will be very, very difficult. And apart from that, again, here also, you may not get the required optimum value. So this one hypothetical experiment is the same I am doing, but here I am doing a bit more systematically. So I fix the flow rate at 1 ml per minute, then change the acetonitrile concentration to 50%, 60%, 70%, and 80%. And I found that at 60%, the separation is slightly better. So I fix at 60, then gradually change the flow rate. In this, I come across somewhere here, I get the required separation, and I complete work and go for validation and find out it is meeting the acceptance criteria and finalize. But again, the optimum is somewhere here, which is not included in my trial. So again, I will not get the optimum result while I'm doing large number of runs. It may be better than the method that is a random method, but here also not possible to establish quantitative relationship between combined effect of all factors and response. So which is needed for, I'll explain it later on, which is the modeling. The modeling is the concept of modeling is the most important aspect of getting out the research. So modeling is nothing but establishing a quantitative relation in the form of a mathematical relation or mathematical equation relating the factors and response. So now this model is required for getting an optimized condition. So in both the cases, the drawbacks are, number one, we miss the optimum condition. Number two, we don't have much information about the process, how each factors is going to influence your process or product. Third, we don't know the quantitative relation between the factors and response as a whole, as a single equation involving all the factors. For one by one factor and the response correlation, we can do it with changing one at a time experiment. But bringing a model or equation correlating all the factors together with the response is not possible. So in both the technique that we are doing now, we may get a product. We can go for, we can marketing, everything is okay. But still, there is something is lacking. What we need is an experimental design. Our factors should cover our optimum. The entire area should cover. And next, it also should give the mathematical relation between the factors and the response. So here I want to make one explanation, the project and research. There is a lot of difference between project and research. Project is application oriented. We are more bothered about the research. We are not bothered about the process. So in project, I want to develop a formula or formulation, a tablet formulation, or I want to develop an analytical method, or I want to optimize a reaction condition, or I want to find out the relation between the various prevalence of disease and the various causes. So these are all projects. I get a product, it meets the requirement, it is having required DT, required disintegration, required hardness, everything is okay. I'm having analytical method, which has a required retention time or a resolution, then why should I bother? So that is project, but research is much more than that. It's a much wider scope than simply developing a process or procedure. Here we want to, or we try to understand the process completely. We want to exactly know the influence of each parameter on the process to identify a critical parameter. The identifying critical parameter is very, very important. And we want to find out the best possible condition, not simply the condition which meets the acceptance criteria. Why I'm telling repeatedly that critical parameter is, I will explain one, the real happened when I was working in industry. That is around 40 years back. A product was manufactured in our Bombay factory. They started a new unit at Chennai. We want to manufacture that process, their same product, same tablet, coating. All the raw materials are same. All the procedure is same. But we could not manufacture the product at Chennai factory, and we have to stop manufacturing at Chennai. And again, it was shifted back to Bombay because the R&D could not solve the problem. It is being run. It is being marketed for 15, 20 years. I think even now it is in the market, I believe even after 40 years. But it could not be manufactured at Chennai factory. What may be the reason? Because they were doing project, not research. Now I understand. After doing all these things, concept, I understood the process they have developed is by project, not by research. So that's why the critical parameters they could not identify, or they did not identify. It may be what you call the surrounding condition, humidity of the room, or control of the conditions are those environmental factors are different. There it was central AC, here it was a different AC. So even the conditions are different. The factory setup is different. So these are the things we will come to know when we are doing research and not project. So my sincere request to research, not project. So that's the outcome of this design of experiment. So now design of experiment is a research, not a project. We are bother more about the process, not about not only the process. I mean, in the case of project, simply we want the product. But in research, we are much more concerned about the process, apart from developing a product of acceptable quality. So whatever we do, the initial trial, the scope should include. So the experiment we are carrying out during the trial stage, it should encompass the optimum point, what we are seeing in the graph. It should be capable of identifying the optimum point by extrapolation if it is not included in the optimum point. So understand, sometimes you may not be might not have included that optimum point in your experimental cover design. But there should be a mathematical way of extrapolation to meet that optimum point. And second most important is it should be capable of modeling from the experimental data. Modeling is nothing but establishing a mathematical equation relating your factors and response, or dependent variable to independent variables. So that should be able to do with involving all the factors in single equation. That is important. So for individual factors, you can find and relate with the response very easy. Concentration versus absorbance, concentration versus your disintegration time. So like that, it is easy to establish for each factor, but the combined effect, that needs some more statistics or some more manipulation, mathematical manipulation. So because only after modeling, we can go for optimization in a scientific way. So now what is this modeling? So modeling is nothing but establishing a mathematical equation describing the relation between all factors taken together and response. For single factor, it is very simple equation, depending upon the type of response. Say, for example, what is the effect of austenitial percentage on retention time? So if there is a linear relationship, the equation will form y is equal to mx plus c. Sometimes it may not be linear, it may be curvature, then it will have a polynomial, second degree polynomial, y is equal to mx square plus m into x plus c. Sometimes it may be 3. When normally this 3-degree polynomial may not be we come across in our study. Usually in any take in pharmaceutical research, cubic response is very, very rare. So far, I have not come across. So straight line, it is a linear response. So the model is y is equal to mx plus c. And if it is a single curve, it is y is equal to m1x square plus m2x plus c. So that is a second order polynomial or quadratic. The third one will get the shape like this, two curvatures. So this we can establish if there is only one factor. But we have to consider a large number of factors. Sometimes in the industrial process, we may not come across, but in some industrial process, we have to consider 40, 50 factors also possible, needed in some conditions. So in that case, this simple representation may not be possible.
Sir?
Yes?
Excuse me, sir.
Yes?
Sir, actually the slide is not being changing, sir. So can we share from here, sir?
Yes, that's what I think.
Yes, sir. Okay, sir. 1 second, sir. Rashida, sir.
Okay, ma'am. I'll be sure.
Full screen pattern, sir.
Can you bring it full screen? No.
Yes, sir. Full screen. Full screen pattern.
It's not coming. Okay, I will proceed. No problem.
Yes, sir. So move to previous slides, no, sir?
No, this okay. Two factor. It's okay. See, if there are two factors also, we can make a mathematical relation or modeling is possible. So again, the general term is y is equal to m1 x1 plus m2 x2 plus m3 x1 x1 x2 plus c. So here m is called m1, m2, m3 are called the coefficient. The value denotes how far it is having influence on the response. The m is more for x, then when x is having more influence, it is critical. So by seeing that value of m itself, we come across how far it is important in the process, what effect it can give. So the same way we have quadratic equation and the cubic equation. So this is possible for any number of factors. Now the two factors also we can depict in the form of a graph. Next. So here it is a 3D plot, two factors at a time. So x-axis, z-axis, two factors flow rate and say oxygenated concentration, and y-axis denote your retention time. So you can say this is more or less planar, a plain sheet. So this we call it as a linear response. There is no curvature. But here you can see there is a curve. That means some of these factors are not having linear response, but it is having second-degree polynomial. It is not linear. There is a curvature. So the graphical representation is possible for one factor and two factor, but definitely not for a higher number of factors. But higher number of factors, we can have mathematical relation. Next. So this is a general form of the equation for any number of factors. So again, it may be either first degree polynomial or second degree polynomial. It depends upon the influence the factors are having. So ultimately, our aim in design of experiment is to establish this equation, either this or this, depending upon the condition of the nature of the variables and factors and the responses. Next. Next. So now let us come to the design of experiment. So it is a scientific way of conducting experiment in a research. It aims at extracting maximum scientific information from less number of experiments. So that's important. We want to get maximum information with the least possible number of experiments. So it provides a means to understand the process better. So it is a tool. Now it is insisted by regulatory agency like ICH and the FDA, US FDA as part of quality by design. So now this quality by design, they are telling the quality has to be built in the process right from the R&D stage, not in the manufacturing stage. So now they encourage or they insist use of these chemometric tools at the development stage so that we can understand the process in a much better way. And it is used for optimization of parameters. So there are two objectives. One is to understand the process, to develop a mathematical model. Using the model, go for optimization. Next. So the concept is not new. It was introduced way back in 1926 in industry, not new. Those days they were doing with manual calculation without any calculator. They were doing with this experiment with fewer factors. But now we have powerful softwares are available where you can do up to 40, 50 factors can also be considered. Next. Now in our pharmaceutical research, where it can be used. Now it can be used very easily. Even some of the open source softwares are also available. So it can be used in formulation development, any formulation. It may be classical or conventional, or it may be new drug delivery system. For any formulation development, it can be used. Analytical method development to study the relation between the cause and prevalence of a disease in pharmacy practice. It can be used for manufacturing process improvement or development. It can be used for optimization of reaction condition to increase the yield. So any type of research involving the study of correlation between the cause and the effect, the quantitative correlation between cause and effect, such study can be carried out using design of experiment. Next. Now, what is the goal in design of experiment? First one is to determine whether a factor or a collection of factors has an effect on the response. So effect means whether it has influence. Suppose if I am changing osteonated concentration, whether it increase the retention time or decrease, or there is no effect. Whether it increase the resolution or decrease the resolution or no effect. So that is the first information we want. What are the factors which affect the responses? If there is a response, what is the extent? Whether it is significant or insignificant or critical. All are there. If it is critical, we should try to avoid, or while doing that experiment or manufacturing process, we take more care to adhere to the value optimized. Third one is there any difference, interaction among the response factors? Sometimes when two factors are together changed, it may have different effect. Instead of changing one at a time, if both are changed, it may have different effect. So that's called interaction. And next one is to establish a mathematical relation or to model. Again, the model is more important. And using the model, we want to optimize the factors to get a desired response. So these are the goals. So if it is analytical method, we want to optimize based upon the model to get the required resolution, required retention time, required theoretical plate count, so like that. Similarly, the goal in the case of a tablet may be different, required disintegration time, resolution, hardness, variability, etc., etc. Next. No. And there are some, next. Go for next. So there are some previous. So there are some terms repeatedly used. Let us quickly go through that. First, factors. It is also called the independent variable. For any experiment, there are dependent variable and the independent variable. In the design of experiment terminology, it is called as independent variable is called factors. And these variables value can be changed independently. And there are two types of factors. One is called qualitative factor, another one is quantitative factor. Qualitative factor that is again called as a discrete factor. For example, the type of column selected. I want C18 column or C8 column. So that is a discrete factor or qualitative factor. Or whether I want to go for starch or gelatin or acacia for binder. So that is a discrete. Whereas quantitative factor or continuous factor is also called as a continuous factor. Now, this is the value we give. Normally, we give a numerical value for this quantitative factor. Next one. Then response. So response is whatever your analytical attribute, all are responses. Your resolution, retention time, rate count, or response. So which is an outcome of an experiment measured quantitatively. So next. Levels. While doing these experiment trials, we fix the quantitative value for each factor. Sometimes we do the experiment using only 2 levels or 3 levels. So these are quantitative. For example, for analytical method development flow rate, I can fix one level at 0.5 ml per minute, another one level at 2 ml per minute. So I'm doing the experiment at 2 levels. So I can do it at 3 level also, 4 level also, 5 level also, depending upon our design of an experiment. So it denotes the number of quantitative value we assign for each factor to run the trial experiments. Next. Then effect. So here it is important. Effect means how it change the response value, retention time. How much it is changed. When I increase 1 ml flow rate from 1 ml to 2 ml, how the retention time decreases, whether it comes from 8 minutes to 6 minutes. That means the effect is 2 units per ml. So this is called effect. The significant effect means more difference between the 2 runs. Next. The interaction. So interaction also, I'll give an example. In pharmacology, we study synergism and potentiation. Suppose if I give 2 analgesics in the same formulation, for example, brufen and ibuprofen and paracetamol, it may have additive or it may potentiate. So additive means it is a combined effect of paracetamol and ibuprofen taken together, no increase or decrease. So potentiation, collectively, they give more effect. Similarly, here also 2 factors. When they are changed separately, the effect may be different. And when they are changed together, then it may cause either additive, that is a synergistic effect what we got in pharmacology, or it may be potentiation. They enhance, or both are possible. Opposite also possible, it may be suppressed also. So that's called interaction. So if the effect is additive, there is no interaction. If the effective potentiated or enhanced or suppressed, there is an interaction. Next. Runs and replicates. So now, ultimately, to develop a mathematical model, how many experiments we are going to run, or how many experiments we are going to conduct. So that's called runs. In the whole process, if I'm doing 20 experiments, then there are 20 runs. And each run will have a different factor levels. We change the factor levels so that total I'll get 20 runs. That changing is done in a systematic way. we will show in the next slides. So that's called runs. The runs denotes number of experiments we are conducting. And the same experiment you can repeat 2 times, 3 times, 4 times. So that's called replicates. Now, sometimes we can do only one. That means called one replicate. I can do it 6 times. I can repeat. That's called 6 replicates. Next. Okay. Now let us come to the important point. I want to proceed with the design of experiment. Whatever may be the design, what I need. First, I need number of factors. And second, I want information about for each factor, what is the highest possible level and lowest possible level. Number 3, whether you want to include only 2 levels or 3 levels. And number 4, expected effect of each factor on response, whether it is a linear or not. So this is important, linear or not. It depends upon the response. We have to select the model. Second, design itself we have to change, because one design may not be suitable for curvature, whether other may not be suitable for linear. So we have some idea. Of course, we can do it with some preliminary experiment. Next, the last one is number of responses to be considered for optimization. So while optimization, whether I want to go for all the possible response, or only certain response you want to consider, so that I will get an analytical method or a formulation which meet or which is ideal or which is a perfect. So these are the informations. So number of factors. If you go for a number of factors, not necessarily you have to include all the factors, and it's not possible also. So as the number of factors increases, the number of experiments also increases. So in some experiment, it will be doubled. For example, factorial design. So if it is 2 factors, it should be run on 4 times. If it is 3 factors, 8. If there are 4 factors, 16. So it will be doubled for each factor. So you have to restrict the number of factors, or you have to do a screening run. There are some other designs are there to do specifically to select the factors. That run you have to do it first. So when selecting the factors, certain things are obvious. Whether you have to go for dry granulation or wet granulation, whether you are talking about reverse phase or normal phase. So these are all obvious, depending upon your physicochemical properties or depending upon your pre-formulation study, you can decide. And next, availability. Suppose in my lab, I am having only C18 column. I have to do with only C18 column. I cannot choose a C8 column or other columns. So like that for pH. For pH, if you know the pKa, if the pH is plus or minus 2 pKa unit, within that there is change. Beyond that there is no net change. So you can easily decide the upper and lower limit for pH based upon the pKa value. Like that, based upon our experience, based upon our knowledge about the drug or your formulation or the process, and based upon the availability of resources, we can restrict the number of factors. And the most important and difficult part is deciding highest and lowest possible level for each factor. So in fact, this is somewhat what you call a tricky level you have to consider and you have to decide. Because we need the highest and lowest level, it should give a sufficient effect on all the response, if there is any effect. So then only our model will be rugged and more reliable. So that is will come with some explanation. You may have to do some preliminary run to find out the highest and lowest possible level for each factor. And number of factors, again, the number of factor level, more the number of levels, definitely you'll get a better model. But again, it increases the number of runs, the resource, the time, how much you can spend. So depending upon that, you can decide the number of levels. But for 90% of the work, for our work, the level is only 2, low and high. And for, of course, for response surface method, it is different aspect altogether, 5 levels, but you may not have that much number of runs. You will see that one. Next, the effect is linear or not. If you have that idea, then you can go for the corresponding better design to get a better result. So next. So of course, there is a variety of designs are available, but the most common are full factorial design, fractional factorial design, response surface design, mixer design, Takeuchi array design, and split pot design. But in our experience, based upon our experience, the full factorial design and response surface designs are most suitable for our study. And we are going to see only these two models. Other model, just we'll see what is some definition only I'm going to give, but we are going to give a full factorial design. And in fact, a response surface design can be considered as an extension of a full factorial design. And some of them, they may start with full factorial design, and if necessary, they proceed to go for a response surface design. So next. And full factorial design, it gives a perfect model. It gives a perfect model. Everything is perfect. But the problem is, it is the number of runs are more. Number of runs are more. As I told you, for each factor, it will be doubled. Number two, it is not suitable when there is a curvature. When there is a curve, after doing this full factorial, and if you go for model, and if the model denotes there is a curve, then this design will not give reliable model. The predicted optimal condition may not be correct. So these are the two drawbacks. Otherwise, the full factorial design is the most efficient design. Next. Now the fractional factorial design, as it denote, so it is can be considered as a screening design. Suppose I am having a large number of factors to be considered, 10, 20, 30. Then I go for fractional factorial design, which drastically reduce the number of trial runs, and resources also will be reduced, so that we can get some idea the important factors to be considered. Then we go for full factorial design. So otherwise, the concept are same. In whatever may be design, I want to make it a point. The difference in the design is nothing but how many experiments you are going to conduct, what is the level, how to fix the level. So that is the only difference among the various designs. Once you decided these number of experiments, number of runs, and number of levels, and run details. So then after that, everything is safe. Next. Response surface design. The difference between full factorial and response surface is response surface is more suitable for when there is a curvature in the response surface. Where it fails in full factorial, so now the same experiments or the same setup can be proceeded further by doing some more experiments. We can convert it to response surface design. Because in response surface design, there are the number of levels are in fact at least 3. Normally it go for 5, so that it is obvious. So if it is a linear, to represent a linear, 2 points are sufficient. But if you want to represent a curve, 2 points are not sufficient. At least we need 3. More the number of points will give better curve, more reliable curve than with less number of levels. So in response surface, effectively, it works at 5 different levels, so that it is more reliable. And since we get more information from full factorial, only thing is the final design will change. It will give more rugged, and it is the best suitable for optimization. Next. And mixture design. So here there are some kinds, of course, in pharmaceutical research. I don't know whether it is there or not. But in the other setup, other area, it is a, for example, if you take a stainless steel, it is having 4 or 5 elements: iron, copper, chromium, nickel, and each one contribute to the final property of a stainless steel. So the property depends upon all the factors. So here we go for mixer design. Next. Next. So here it is. So this I will give one analogy, Takuchi array design. Say I'm having a pain, body pain. I take a analgesic. When I take analgesic, I get hyperacidity. To control hyperacidity, I take a proton pump inhibitor or antacid. So this is a process. So here, to control the side effect of analgesic, I take an antacid. Similarly, in some process, some factor produce noise. Apart from beneficial effect, it produce noise, similar to our analgesic. To control this noise, I add another factor, like our antacid, that's called control factor. So the Takuchi array design is mainly to find out the optimum level for control factor. So here, this also we are not normally come across in our pharmaceutical research. Next. And split plot design, again, it is only for industrial setup. In industry settings are very difficult to change. For example, the huge oven, industrial oven, or if you want to do carry out some research in field, agriculture field, there these things we cannot be changed. Hard to change variables. So the split plot experiments are conducted. So these are all only, I mean, we are not going to see much about it. Next. Okay, so if you take full factorial design, we carry out trial runs at all possible combination of factor setting. The number of runs depends upon the number of factors and number of levels in each factor. It is given by AN into BN into CN, where AN, BN, CN are levels for factor A, B, and C. So suppose if I want to run 3 factors, say pH at 3 pH level, and 3 flow rate, and 3 astonated concentration. Total, I have to do 27 runs. So again, if I want to repeat, if the replication is at 2, then 54 runs. So like that, it will multiply. So these are number of experiments are decided by the number of level for each factor and total number of factors. Next. So the same example I told, I want to conduct a development analytical method. I want 3 variables or 3 factors: pH, flow rate, astonated concentration. I want to keep the pH at 3 level, 3, 7, and 10. And flow rate, I want to maintain at 2 level, 1 ml per minute and 2 ml per minute. And astonated concentration, I want to have 3 levels, 30%, 50%, 70%. So the number of levels are 3 for pH, 2 for flow rate, and astonated 3. So the total number of runs required is 3 into 2 into 3, 18. If I want to do 2 replicates, it comes to 36. And most of the factorial design, though we talk much about levels and all, more than 90%, we do 2 power k full factorial design, where 2 denotes 2 levels and k denotes the number of factors. So levels normally we restrict to 2, not more than that in a factorial design. Next. So here, as I told you, 2 implies all the factors are used at 2 level. Here is the number of factors. The number of run required is given by 2 power k. And here, one important point, please note it. Though we keep it at 2 levels, normally we don't use the actual value. We give coded value. Low level is considered as -1, and high level is considered as +1. In other words, in computer language, the values are normalized between -1 and +1. So this will give make the calculation much easier and understanding the process much easier. Next, how to proceed? First, decide the factors to be included in the study. Next, decide high level and low level for each factor, and decide the response to be considered for optimization. If needed, perform fractional factorial design to decide factors and critical factors or important factors and levels. Then finalize the design matrix and perform the experiments. We'll give some example. We'll see some example. Next. First, let us take, we want to optimize a condition for involving only two factors. That is acetonitrile concentration and flow rate. Low level is 40%. We call it as -1. High level is high value is 80%. That is +1. Similarly, flow is 0.6 ml per minute, -1. 2 ml per minute is a higher level is +1. And we want to consider three responses: retention time of first peak, retention time of second peak, and resolution. So because the retention time of first peak denotes how fast it is coming out of the column. Because if it is coming less than 1 minute, then most probably it will be disturbed by the solvent vent. Second peak normally decides the run time. More the retention time, we have to run more. When the first peak is coming at 2 minutes and the second peak at 8 minutes. So the 6 minute is unnecessary. So we want lesser second retention time. So we want to optimize to that level. And of course, resolution we need sufficiently to so that there is a baseline separation. Next. So this is the design. So two level, two factor, that are 4 experiments. 4 experiments. First experiment, both are low level. Second experiments, one low, next higher level. Third experiment, low, higher acetonitrile, and I think it is a mistake. It is a -1. Third one is a flow is a -1, and fourth one is a +1 and +1. So we have to conduct the experiment and fill the data. We have to conduct 4 experiments and fill the data to proceed further for analysis. So this is the way we design. So it is a more structured design. So if you have properly fixed the higher value and lower value, you are encompassing the optimum condition. Next one. If it is 3, we are adding one more pH. 4 low level, 10 high level. Next. Same. -1, -1, -1, -1, -1, +1, -1, +1, 1. So these are 8 runs. So this is the value conduct the experiment 8 times. Next. I can add one more parameter, column temperature. I can run at 30 degrees Celsius and 50 degrees Celsius. Next. Now there are 16 runs. So this is the way it is distributed. So it is not a random or one change at a time. We are changing everything systematically so that we create all possible -1 and +1. And we arrive at some mathematical model that involves a lot of statistics and calculation that we are not going to see further. I mean, that in detail. Next. Next. Go for next. I think it is again repeating, I think it is repeated. Go for next. Next. I think it is repeated. Next. Okay. Go to previous one. Previous. So next. Stop. Say for Previously it was coded, now it is actual. So in actual law, we are conducting 8 experiments for 3 factors. We have conducted and the results are given next. So these experiments carried out and these are the results. First run, 40% acetonitrile, 0.6 ml per minute, 4 pH. The retention time of first peak was 4.1, second peak was 7, and the solution was 5. When the second run, like that, all the 8 runs we have done, we have completed the experiment. So our experimental part is over. So experimental part, the important, decide the factor, decide the level, decide the replication, design the matrix, finalize the design matrix, carry out the experiment. Our work is over. Then what to do with this result? Next. Now, we have to find out the mathematical model for each response first. For each response, for retention time 1, the mathematical model. Retention time 2, mathematical model. Resolution, mathematical model. That is a chemical equation, the mathematical equation. So that is involves some statistics, some calculation, let us not bother about it, and the software will do. So that's what we have to find out the mathematical equation modeling. Then we go for graphical representation of the model to understand the system clearly. So as I told you, graphical representation is possible only for 2 factors. So even for if you are carry out the reactions for experiment for 3 or more factors, still we can visualize by taking 2 factors at a time. Then we have some idea. Then we go for the so-called perturbation plot, which shows how far the each factors are effective on each response. Then we go for interaction plot to know the interaction between factors. Then we go for optimization of parameters to get desired response. Next one. You need not do any calculation for this. There are many commercial softwares as well as free open source softwares are available. Now, whatever we are showing is obtained from Design Expert software DX7. Commands are there. You need not to. Once you are clear about number of factors and levels and responses, your work is over. Everything the software will take care of. Even design matrix, it will give. You need not make the design. It will give the design matrix. Next. So this common equation, R is response, and P1, P2, P3, P4, P5, P6, P7 are called coefficient. A, B, C. A for acetonitrile concentration, B for flow rate, and C for pH. And AB terms called interaction factor or interaction term. Interaction between A and B. Is there any interaction? Interaction between A and C, interaction between B, C, and interaction between all the 3. Like that, we get 4. In our present case, we get 3 such equations. 1 for retention time, 2 for retention time 2, 3 for resolution. Next. So as I told you, by seeing the coefficient, that is P1, P2, P3, P4, the one which is having more p-value is having more effect on the response. So that is, if it is very high, we should be very careful, because it may alter the result of experiment, or it may affect the process to affect the quality of the product if there is small change. That is called critical factor. So by seeing that p-value, we can get some caution about each factor. And in this software, if the sum of the p-value is insignificant, statistically insignificant, such p will be eliminated or such terms will be eliminated automatically by ANOVA. Next. So this is the actual model for retention time 1 plus 2.64 minus 0.41 into A minus 0.89 into B minus 0.038 into C. So this is the actual model or actual equation. So this the first one is in terms of coded factor -1 and +1. You can see the 0.89 into B. The P is more for B. So B have larger effect, that is the flow rate is having larger effect on retention time. The same equation in terms of actual value. So the first one is the white, the color in white is in terms of coded -1 and +1. And the green one is the equation is based upon the actual value, that is 40%, 80% low level and high. And here there is no term for ABC. That means there is no interaction between ABC term. All the three is not having interaction. Next. This is for retention time 1. We have taken a flow rate and the austenitial concentration, a 3D plot, and the surface is more or less planar. There is no curvature. So now for this alone, for if you take only these two, the factorial design will work very well. There is no need for going for response surface method. Just it is planar. Next. So this also planar. So we can go for optimization. So this is for austenitial concentration and pH. The first one is austenitial concentration and flow rate. Third one. Next one. So here there is a slight curvature. When you take the pH and the flow rate. So these are the information. By seeing this plot, we come across whether it is planar or if there is a curvature. If there is a curvature, now all the three, there are some curvature, but not more significant. So the factorial design will very well work for prediction. Next. The same way, we can go for the effect. So you can see that B is having more effect. The flow rate is having more effect on the retention time 1, and austenitial concentration is having less effect, and pH has no effect on retention time 1. So the drug 1 is independent of pH. So this very, very important information we get. This is called perturbation part. So if you want to keep the retention time, we should be controlling the flow rate very accurately. Of course, we get but since it is a common problem, it will not be more problem. When you are going for, say, formulation development, say concentration of SLS on, say, disintegration time or whatever it may be, it will have a lot of influence. Sometimes it may fail. Say hardness also, if it is that much critical. So that we can see very easily from this perturbation plot. The next is on retention time 1. Next. So now here you can see austenitial is having opposite effect. So increasing the concentration decrease the retention time, whereas it increase opposite effect for retention time 1. And here also the pH having little effect, and more effect is for this flow rate. So here the effect of austenitial concentration on RT1 is less, but at RT2 it is having a more effect than on RT1. Next one. It's having a more or less same effect as that of, no, it is, we go for next one. Oh. So if you take a resolution, interestingly, only 2 lines. That means the resolution is completely not affected by pH. That's why the term is not included in the equation. Okay, so this implies pH is having no effect at all. For at least for R1, R2, there is some effect, though it is not significant. There is some effect, but it is completely missing. So the resolution is completely independent of pH. The next one. So this is called interaction plot. So interaction between interaction for the response is retention time 1, and interaction between accelerated concentration and the flow rate. So when these lines are perfectly parallel, there is no interaction. Completely, there is no interaction. If it is not parallel, there is interaction, but how much it is interaction? So you go to the next one. Next. This one. You can see it is crossing. That means there is a great interaction between flow rate and pH as far as your retention time point is considered. So this, whenever there is an interaction, normally it leads to curvature, small curvature. But how far it depends upon the individual effect. So now the first one, we got the shape of the 3D plot, which gives information whether there is a planar or curvature. So if it is curvature, your factorial design will not work. Next, the perturbation plot gives about the critical factor, which factor is to be controlled properly during the process or the procedure. Now, the third one is it gives the interaction between the factors. So like that, for each response, we get information. I have shown only for retention time 1. For RT2 and response, we can have a different equation, different graph, and we can compare. Next. So these are the inferences told already. Retention time, acetonitrile and flow rate have significant effect on RT1. Increase in the acetonitrile concentration decrease the retention time, and increase in flow rate also decrease the retention time. It is obvious when you increase the flow rate, the retention time comes down. There is a small interaction between the acetonitrile and the flow rate, but not statistically significant. Next. The same is for interference for RT2. Next, RT3. Next. Then, okay, we have understood the process now. We have developed the model. From the model, we have come to know what is the type of effect, whether it's a planar or curvature. We have found out the critical parameters. We have found out the interaction. Next, we go for optimization. For optimization, we fix certain criteria for variables, both independent and dependent. For both factor and response, we fix the criteria. So in this model, in this experiment, we are designing the criteria like this. For percentage of methyl acetonitrile, we didn't fix any criteria. Simply, it may have either between 40 to 80 anything. Similarly, flow rate also, we have not fixed any criteria. 0.6 to, that's what we have done, low and high. And pH in range, again, it is a 4 to 10. But the retention time 1, I want less, minimum or at least 1 minute and maximum 2 minutes. So that my peak will not come, first peak will not come before 1 minute. So there will not be any interference from the solvent front. And I don't want higher retention time because it will increase the runtime. So next, for criteria retention time 2, I want as minimum as possible, so that the runtime will be less. And the last one is resolution. I want 3 to 5 because less than that may not be, baseline separation. More than 5, it is not necessary. So this is the optimization criteria I have fixed. And if you give this criteria and based upon a complete, programming algorithm, it will select the conditions required for a to meet these criteria. Next. And these are the results I got. If I fix the main parameters, 40 ml per minute with 40% of acetylnitrite, 2 ml per minute, pH 10. I will get a retention time of 1.98, and for second peak it is 4.987, and the retention will be 4.95. The desirability. So it is a statistical term. So by ANOVA, it will decide how much it is accurate. The more desirable means more accurate, more reliable. So 1 is maximum, 0 is the least. So here I got with the desirability function of 1. So like that, I have optimized. You can choose any of these so that you get the required retention time and the required resolution. So it is simple. So our work is again and again I'm telling you have to decide the parameters, low level, high level, and how many levels you want, how many replicates you want. These are the things you have to decide. Next. Now, response surface method, how it differs. So we are not going to bounding, it is an extension. So it is a more advanced technique. It is often used to refine the model already you have generated. So for factorial designs, already we have done. I want to read and refine it. Then I can go for a response surface method. Especially if curvature is suspected. So I am suspecting factorial design, even though it is not clear, I am suspecting there is a curvature. So I am not satisfied with the full factorial design. Then I will go for RSM design. In the given example also, I suspect there is a curvature. It's not a perfect plane. And again, there are two designs are used under response surface method. One is called the central composite design, and the other one is box Penton design. So again, that CCD is most commonly used. We are going to see only about the CCD only. Next. So next, we go for next. So as we have seen in the factorial design, if it is a planar, there is no curvature, we can go for a factorial design, optimize, use that value. If there is a curvature, so here it is, I have shown this just to show the curvature, how it, a full curvature, how it looks like. What we have seen in our example, it is not a fully planar. At the same time, fully planar will give the same color. So normally the presentation is like that. Different color is at different level. So next. So it is a planar one. That's what we get. Planar also, it is planar, but there is small color shade different, blue and green. It should be a perfect same color. There is a planar. Next. So in our model, clear cut, it says there is a curvature in our model, what we have generated. So we suspect there is a curvature, so there is a need for CCD. Next. Where we go, use factorial design to get close to the peak. We come somewhere nearer to the peak. Then we go for RSM to climb it to the top. So this is application of a response surface method. Next. So it is the most commonly used RSM. Factorial design is not suitable model when response surface has curvature. CCD is a refined factorial design. It is an extension of design. When there is a curvature in the response surface, it is used. It is built upon factorial model by adding additional experimental points. Same 8. If there are 3 parameters, same 8 points, 8 runs, but we add additional point for center point and center point and axial point. Next. So it is how to build a CCD. Let us assume I am doing a full factorial design with 2 factors. Then my runs are 4. there are 4 experimental points: -1, +1, -1, -1, +1, +1, +1, -1. So this is a factorial design. Then I built upon this. Now add some more experimental points in a scientific way. Next. Now I add a center point. 0, 0, that is denoted as 0, 0, -1, +1, 0. That is average of both high and low for both factors. Now this center point, I make a replicates of at least 6. Because the center point is most important point in this design. I don't want any error in that point. So I repeat that experiment 6 times in that point alone, but all others are only one replicate. So there's one important point about RSM. Next. Then I add another points, another 4 more points. That's called axial points. So it is the value of axial point is 1.414. So that's called alpha value. -1, +1, and the axial point is either plus 1.414 and minus 1.414. So now I have added 4 more points. Okay. So 4 + 4, 8, 8 + 6, or at least 5, 13, or 14. Why this type of distribution? How it has come? Why that alpha value 1.414? Say for 2 factors it is 1.414. For 3 factors it is 1.682. So that is a scientific value of way of calculating that. So that go to the next slide. You can see all the points are in a circular except the center point. Or it forms a circle with equidistance. So that is the meaning of alpha value, that 1.414. If it is a 2 factor, it will form the periphery of a circle. So if it is a 3 factor, instead of circle, it will be a globe. All the factors will be, all the experimental points will be on the surface of a globe. Similarly, at higher factors, it is called hyperplane. We cannot express in terms of models or graph. So this is why it is called rotatable. It is a spherical, and it will be a more rugged information, more rugged model. So next one. Next. So again, previous. It is more or less same. For CCD design consists of 2 power k factorial points, as we have seen, and 1 center point, usually 6 replicates, and axial points 2 into k. If there are 4 factors, 3 factors, the axial points are 6. For each factor, 2 axial points, plus alpha and minus alpha. It is 1.414 for 2 factors and 1.682 for 3 factors. It is calculated as 2 power k to the power 1/4. Number of factorial points raised to power 1/4. So that is the value for alpha. Next. So this is the design. That is whatever we have seen in the graphical. It is for 3 factors. The first 8 are factorial design, as we have seen full factorial. The next one is a center point, 6.6 replicates. Same is repeated, that is important. And 6 axial points, 6 + 6, 12, 12 plus 8, 20. There are 20 runs. Next. The remaining procedure is same. Once you have decided this is, perform the experiment, feed the value, then get the answer. Similar, the everything is exactly same as that of factorial design. Since I don't have data for this 12 experiment, I could not present the graphical texture, but everything is same, ditto same, 100% it is the same. So only our design means fix the experimental points or runs, and other things analysis is same. And there is one caution: confounding variables. So we have considered so many variables. Okay. And there is one aspect called confounding variable. You should be very cautious about it. I will explain with small example. A study was conducted to assess the prevalence of sunburn among persons fond of taking ice cream frequently daily. There is a study. The person is having more ice cream, whether they have more sunburn or not. So that is the objective. So they carry out, volunteers as usual, all these inclusion criteria, exclusion criteria, everything was fixed. And the experiment was, sampling was done scientifically, and the experiment was conducted with 100 samples. They found that is a significant increase in the prevalence of sunburn among the persons taking ice cream. So the study concluded that ice cream can increase the chance of sunburn, but it can be wrong, and it is wrong. How? Next. It is not ice cream, but it is a summer heat. Because of the hot summer increase the urge for taking ice cream. So the person is going to ice cream shop frequently in the sun, exposed to sun, and because of that, he is getting sunburn. So understand. So the hot summer is having effect both on factor as well as response, both on independent variable and variable. So here heat is called confounding variable, which has effect on both factor and response. So confounding variable has effect on both factor and the response. So be careful to avoid confounding variables. So of course, for our formulation development and analytical method development, normally, except the extraneous condition like excipients, when you are using the process like humidity of the room, there may not be any effect. And most probably, humidity of the room is one of the confounding factor if it's not properly controlled. So next. So these are the various softwares available. Minitab, Design Expert, Start Easy, DOE Fusion, Mode, Nemrod, Unscramble, SAS, SPS, all these things. So these are all paid software. You have to buy it. So next one. So these are the free online resources available. Only Scilab and R competitions are freely available. Of course, I have not tested with that, but it is available. It may not be that much rugged as that of paid software, but still you can use at least to learn, and you can start your work. And once you are confident, you can go for buying the software. Next. Next. To conclude the advantages of your design of experiment. So reduce cost, it gives save time, reproducible, more rugged, and it is more efficient. You can immediately follow checkup using online software, and you can start using this technique in your research. Next. Thank you very much. Thank you very much.
Thank you so much, sir, for highlighting the basics of design of experiments, as well as their applications in pharmaceutical research with examples. And I request Dr. K. Naveen, sir, to present the concluding remarks for the wonderful session. Over to Dr. K. Naveen, sir. Naveen, sir? Sir, Kannan, sir, we have a few queries with us posted by our registered participants. First question is, what is the protocol to select a factorial design? Sir, you are in mute, sir. You are in mute, sir. Please.
Yes.
Yes, sir.
See, protocol means, as I told you, First thing is decide the variables. So while deciding the variables, that is the most deciding the variables and the levels is most important in any design of experiment, not only factorial designs. If you are clear with your number of factors and levels, then the matter is simple. But it requires some experience, because initially you find it very difficult to, of course, the variables, factors we can decide to some extent, but levels it may be difficult to decide, because if the levels is not fixed properly, normally the result may not be as the prediction may not be as accurate as needed. So for that, normally what I do is at least I take some preliminary runs, 5 or 10 runs I used to take. And again, when you take factors, many factors in our college setup, we may not have many columns. We may not have column temperature, O1. So, and again, we normally start with acetonitrile, because methanol normally gives back pressure issue. So these are some experience we consider, and we start with the remaining factors. And once the factor is decided, then comes level. To decide the level, and one thing is for pH, we can go for the pKa of each compound, and we can come to some level of pH. So considering a pKa of all the components in the mixture, if there are 3 components in the mixture, take the pKa of all the 3 drugs, and accordingly, normally the pH should be away out of plus or minus 2 pKa. If the pKa is 4, if the pKa is 5, normally we select the pH less than 3 or more than 7, so that it will be either completely ionized or completely unionized. So the peak broadening effect will be less. So like that, some knowledge of physical chemical property. In the case of, say, formulation development, your pre-formulation study, it can give a lot of information. What are the parameters to be selected? What is the level of each ingredient? And some of the things are fixed. So you know very well for a disintegrant or SLS or AT, all these things, we have some idea. So it requires some design. Once these two decisions are these two are decided, then it is everything is easy. Everything is software is going to do, and we are not going to bother about this calculation, how this calculation. And if you want to know how it is exactly calculated, there is a book called Pharmaceutical Statistics by Bolton. I think it is in Anna University Library, it was there. Bolton, Pharmaceutical Statistics. It gives separate chapter on factorial design. It gives with formulation example, it gives. And now you get a lot of example in the net also.
So this question is raised from Ms. Durga Bhavani Madam from Viper, Narsipur. I hope your doubt is being clarified now. Thank you so much, sir. And another question is from S. Nagalakshmi Madam from Sri Ramchandra Faculty of Pharmacy, Srihar, Chennai. Her question is that how to fix levels and optimize. That's what you asked.
That's what I was explaining.
And,
I think,
question.
say, Arifa, most of the doubt would be like this only, these two only. Most of the, because initially everybody will have doubt like this. So there are 2 ways. One is run fractional factorial. So fractional factorial will reduce your number of runs to half. For 3 factors, you can complete with 4. So the design, it will be software will be the design, how to do it. Only thing is you do the command. So you can run a preliminary run, you can make with a fractional factorial. Then you go for full factorial. Then you can go for RSM, response surface method. You can go.
Thank you, sir.
So if you are confused, and if you don't have any idea about it, and if you have resource, I strongly suggest go for fractional factorial design. Even you can give 5 or 6 factors, you can include and run it. With 10 runs, you can have some idea. Definitely, it is not the final, but you can definitely get some idea. Then you go for either directly, you can go for RSM, CCD.
Another question is from Mr. E. Bhargav research scholar from Raghavendra Institute of Pharmaceutical Education and Research, Anantapur. Sir, question is that need of power in screening designs, that is why it need to be maintained above 80%.
What?
Need of power in screening designs, that is why it need to be maintained above 80%, especially in design expert software. And if p-value greater than 0.05, can it be considered, or how it can be adjusted or not?
No, it's not clear. What is 80%?
80% in design expert, sir.
No, still.
P-value greater than 0.0.
P-value.
Yes,
So
regarding
it depends
p-value,
upon
sir.
it depends upon the confidence limit. Normally we go for a 5% confidence limit. We fix it. So it is a normal procedure for a fixed confidence level.
Thank you so much, sir, for the wonderful session. We have our principal ma'am with us. Now I invite respected principal madam to say a few words about the session. Answer.
Good afternoon, sir. I am Dr. A. Sunita.
Good afternoon.
Thank you so much, Kanan Garu, for sparing your valuable time with us. I hope students have, participants have gained so much knowledge on usage of DOE. You have given a clear-cut picture of why DOE is so valuable. Sir, I have, out of my passion, I would like to know, actually, you are so highly experienced and emeritus professor. How do you accommodate with the latest technology? Actually, we all are looking about the DOE. Now we are ready to guiding our students to go for usage of the DOE software. Let us know, because you are the inspiring personality, how to acquire with the advanced technologies for the younger generation.
See, now this DOU may become compulsory, because now gradually that is QBD, quality by design.
Yeah.
Though it is not mandatory to use, but they insist to go for scientifically designed experiment right from R&D. So previously the regulatory agencies were bothering only about manufacturing and quality control and marketing, but they now started looking about the scrap. From day one in development of a new drug or formulation, they want a scientific way of conducting the experiment. So in that aspect, our students, I think in pharmaceutics, MPharm, there is a chapter on it. I think MPharm, the new syllabus. So there's a computer-aided drug development.
Yes, sir.
I think it
Recently,
is,
we came to know, actually,
yes, yes.
I have published one paper in the
Yes,
last
yes,
year about the usage of DOE for method development.
Yes, yes.
But I was wondering, by seeing you, how, in which way you are expertise in the latest technology.
No. It's not very difficult, I think, madam. It look very hi-fi and all.
Okay.
Many of things we think like that. For example, out of my experience, after my retirement, I got some interest on artificial intelligence. Though we were doing in my service, some PhD students are working on it. But it's not that much easy. Probably, I mean, you spend some time and everything available online. Without spending a single paisa, I learned, I developed one software for, again, another development. One MPharm is completed. So we people think when the moment, I also like that, the moment we see the equation model, then we get confused. So that's a mind block we get. So there's nothing. Initially, you may find it a bit difficult to understand the concept and how to proceed with that. But as the time goes, you find it very difficult, very easy for that. And software, this design expert software, the trial version is available for 1 month. And I think it's not much costlier also. I think we purchased in our department that time, some 15 years back, it was for 50,000, some that only. Exactly. So as an experiment, I mean, for college, I think I strongly suggest you can buy, and it forms part of your syllabus, and even you can regular practically can include.
Actually,
No
we
need for
downloaded 1 month free trial version, sir.
it is free trial available. So you said today you use your laptop, next time Arifa laptop 1 month and Sar laptop 1 month. So 3 months you get that. Then you can go for buying, or you can go for that open source.
And let me know which is the user friendly. There are so many softwares you suggested.
No, but I have used only Design Expert. It is quite user friendly.
Which
I have
one,
not
sir?
used it. Design Expert. Design Expert.
Okay.
Design Expert.
DX7 is different.
DX7. So that is a version.
Okay.
Yeah, DX1, 2, 3, 4. Actually, we purchased DX4. Now it is DX7 or it has come.
Yes, 7. Your talk is really illuminating all of us, sir. Thank you so much.
Thank you very much, sir, for the wonderful session.
Thank you.
Very
Thank you, sir. Thank you very much, sir.
Thank you.
Thank you very much, sir.
Thank you.
Professor Kannan, sir, for enlightening us on qualitative methods and quantitative analysis and their responses with our daily research and at the industry level also. You have discussed about different columns, effect of mobile phase, buffer, pH, importance of flow rate, their interactions and influence in detail, and also about the design of the experiment, development of the process, establishment of the mathematical modeling, particularly about critical factors versus responses, and explaining us about each factor, its importance of the pKa value. Sir, you have explained us in detail about different factorial designs, particularly about parameters of high level and low level factors and their responses, how to analyze the graphical representations of the model to understand the system, optimization of the method by ANOVA with an example, response of surface method for refining the optimization of the method with response to surface plot. Sir, you have discussed about the building of CCD factorial design without errors with an example, confounding variables and different software available. I once again thank you very much, sir, on behalf of KVSR Siddhartha College of Pharmaceutical Sciences for enlightening us and sparing your valuable time with us. Thank you very much, sir.
Thank you so much, sir.
Thank you, Kananji.
Thank you.
Thank you. Thank you, sir.
Thank you, Dev. Thank you for giving the opportunity. Okay.
Can I
Shall we
conclude
leave?
the session?
Okay.
Yes, sir.
Conclude the session. Huh?
I'm concluding the session, sir. Thank you,
Okay.
sir.